So chapter 6, this is where we're looking at our first combinational logic gate. And then we came up and went through these guys. So this is basically the makeup of exclusive ORs and exclusive NORs, but that's not very important for us to understand. What's important to understand is that this gate, we call it a gate, but technically it is a combinational logic circuit because it's used so often. These two are used so often. So what we do is for the symbol, these guys will only have two inputs. So we say an OR gate could have two or more inputs. Our exclusive gates only have two inputs. There's no such thing as a 3-input exclusive OR gate. These are our digital comparators. So what we do when we compare is we see if things are equal, right? You understand? So what we're doing is we're comparing two bits coming in on the inputs. Yeah, we only have two. Yeah, we have an exclusive OR, and then we have an exclusive NOR. These guys will only have two inputs. We start out, the symbol for these gates, these are combinational logic circuits, but we call them gates. They have their own symbol. So we start off with a symbol of an OR, and then what we're going to do is we're going to put this shadow back here. And then this is our exclusive OR gate. Now, we abbreviate this XOR. That's why it's abbreviated. And we'll run into this. So if you take motor controls also, we can create this, this thing using relay contacts. Now, the symbol, and these guys are looking for if the two inputs are the same or if the two inputs are different. It's going to give us an output. And what we got to do is figure out what indicates they're the same and what indicates they are different. Now, what the symbol is, the symbol shows us what we get if they are not equal. So this guy says we'll get a 1 if it is not equal, because I don't have that circle right here, right? You understand? So this, everybody okay? So if I was going to draw a truth table, and I call this A, B, these guys will only have 4 entries in a truth table because they only have 2 inputs. No more, no less. There is not a negated symbol. There is not a negative symbol for an exclusive OR gate. So that push and bubble things we talked about only applies to the 5 basic gates. There's no such thing as a negative exclusive NOR or an exclusive OR. So if this shows what I get when they are not equal, what would I get here? Well, this shows me I get a high if they're not equal. So are they equal? Okay, so the output would be 0. Are they equal? No, so the output would be a 1. Are they equal? No, the output would be a 1. Are they the same? The output would be a 0. So I can look at the output of this gate and I can tell if the inputs are the same or I can tell if they are different. On this gate, if they are different, I get a 1. If they are the same, I get a 0. So what we do when we do our equation is we draw when the output gives us a high. So what does the output give us a high? It gives us a high if A is low and B is high, or if A is high and B is low. And that's the Boolean equation for an exclusive OR. I think we're going to use a 7486 or a version of it, 7486. And hopefully by now, I think we've talked about it before. 74, this is for commercial grade TTL. And then we came out and we had what we call the standard series. So when we talk about TTL compatible, we're talking about being compatible with what we call the standard series. So we're going to use the 7486, which is an exclusive OR gate. But you might see a 74L86. Now this is still the same gate. It has the same truth table. It has the same equation. Y'all understand that? But what this tells us is these center designators are going to give us the speed and power characteristic of the chip. So we have different families of 7400. So a 74L86 would be a low power, low speed. Does that make sense? So we'll look at these different families within these. So we got, this is why when you look at data, digital data books, they're used because the characteristics of an L, the electrical characteristics of an L family would not be the same as a standard family. So they'll have a different data sheet. Not the pinout. The pinouts are the same. Y'all understand that? Yes or no? Now, in fact, the next chapter we're going to go into is 9. Chapter 9, where we'll start looking at some of these data sheets and understand the difference between these different families. They are the same. A 7486 is a 7486. It is a 2-input, quad 2-input. If it's in a 14-pin DIP, it would be a quad 2-input exclusive OR. So if you're looking at the pin out, you don't care if it's an L, you don't care if it's an LH, L, you don't care if it's an LS, you don't care if it's an HC, you don't care if it's an HCT, you don't care about that. If you're looking for the pin out. Now, if you're looking for how much current it can drive for a high, what is a high, what is a low, then you're going to have this is where it comes into difference. Not the pin out, but the electrical characteristics of the gate are going to be different. So you want to say, okay, can I turn on a light bulb with this? Well, a 7486, not a light bulb, a 7486 might be able to turn on an LED directly. A 74L86 probably won't. So that's where you'd get into differences, right? You understand? So we could say a car, you know, all these cars, if I've got an HHR, how many HHRs out there? Well, there's 1,000 of them. Some of them are the same, and some of them are what? Different. So that would be like the options on a car. So you go out and buy a car. And if you buy so you have the standard series. That's the series with no options. Well, you can buy the same car that you got different options, but they all have the same doors. They all have the same windows. They look the same. And most of the time, you just can't tell the difference between the options. So that's basically what the L and the LS means. That makes sense? So it'd be like buying a car. Then you have options, and that would be where your L and your LS and your H series and your HCTs and all those come into play would be the options of the car. You pick one and hold it up in your hand, it's a 14-pin DIP, they all look exactly the same. And the pin out would be what? The same. So this is an exclusive OR, guys. So if I use this guy, it is going to give me a 0 on the output when the two inputs are the same. It gives me a 1 when the two inputs are different. So these are digital comparators. And there's the Boolean equation, which says I get a high if the two inputs are what? Different. That makes sense? Yes or no? It's a 2-input exclusive OR. And they're all 2 inputs. That's the big difference. So if I say an OR, if I said how many inputs could an OR gate have? And you'd say 2 or more. I said how many inputs could an exclusive OR gate would have? And you would say 2. Because these are our comparators. Now we can make it compare more. So if I came over here and did this, and then I brought this into an AND gauge, and then I call this A, B, C, D. And if A and B are equal and C or D are equal, then the output here would go high. That makes sense? So we can expand the capabilities of exclusive ORs by adding ANDs to them, or negative ANDs. So you'll see this done. And of course, comparing is very, very important to see if things are equal. So if we compare, if an exclusive OR only compares 2 bits, and I need to compare 8 bits to 8 bits, then we can do that, right? Y'all understand that? And of course, since this is pretty popular, odds are they've made integrated circuits that do this, right? Makes sense? I don't know how this got in here. We need to find the exclusive NOR first. So the exclusive NOR. So this shows me what I get when they are not equal. Oh, I see. Figure where that's out. So that means these right here would be not equal. So that would give me a 1, and that one would give me a 1. So this gives me a high, gives me a low if they're not equal. It gives me a high or a 1 output when they are equal. It's just the opposite of an exclusive OR. So when we draw our Boolean equation, we draw it always what's required to get a high output. So this one looks pretty simple. So it says we get a high output if they are the same. So that's the Boolean equation for an exclusive OR. Exclusive NOR. So it says if A and B are high, or if A and B are low, then the output would be high. This guy is a little different because this guy says the output's going to be high when they are not equal. This says the output's going to be high when they are equal. Right? That makes sense? So this is a timing waveform. I wish I didn't have this down here. I would like to come back and figure it out myself. So this guy gives me a high when they're what? Not equal. This guy gives me a low when they're not equal. So high when they're not equal, right? You understand that? So here they are equal. So the guy would be a what? A low. No, we're going to do the top one first. So a high if they are not equal. So this guy right here would go right there. So here they are equal, right? See that? Ooh. They're not equal here. They are equal here, right? They're not equal here. I'm sorry, they are equal here. So here they're not equal, right? Here they're not equal. And here they're equal. And then this guy would give us just the opposite. So this gives us a low if they're not equal. Here they are equal. Here they're not equal. Here they are equal. They're not equal. Oops. They are equal. What? So this is exclusive OR. Of course, that would be the symbol right here, right? It shows us what we get when they're not equal. So we'd start off. So are they not equal? Okay, so we'd start off what? Are they equal? So we go to low, right? Are they equal, equal, equal? What would happen here? Go back high. Here they're not equal, they're not equal, they're not equal. Here they're equal. Here go low. Now finish it out. We're okay. Oh, I'm sorry. Yeah, I'm sorry. I thought it was equal. I'm sorry. Good job. What does the instructor say? Yeah, I just tested you. So just looking at the output, I would be able to tell right off the bat when they're equal and when they're not equal, right? Now, if we did the same waveform with the exclusive NOR, it says I get a 0 when they're not, right? So here they're what? Yeah. So we'd start off low. Here they are. It would go what? High. Here we do what? Go low. And then it should finish out. So how many inputs would the exclusive gates have? 2, right? And the output symbol, if it's got a bubble or it don't have a bubble, this is telling us what we get if they are not equal, right? Are we okay? Now we use these things for all different types of things. There's something that we refer to. So when they started trying to send digital information through medias, like the air and of course cables, what they wanted to do is they wanted to come up with some method where they could verify that the data being received was the data being transmitted. And they didn't want to waste a lot of bits to do that. So the first method they came up with, something referred to as parity. So they say, okay, we're going to send data, and let's just use 8 bits. So 8 bits, if I'm using 8 bits, it would look like it would mean I could send 256 different combinations, right? Y'all understand that? 2 to the 8. And how do we calculate the number of combinations we could have on the inputs to a digital circuit? So right now we're dealing with gates. We're moving into digital circuits. We're moving into combinational logic, and eventually we'll get into more complex circuits. So when I look at a digital circuit, and then I look at the number of inputs. So normally over here in the good old USA, when we draw schematics, we draw our inputs on the left, and we draw our outputs on the right. Right now we're dealing with things that's only got one output, but eventually we're going to deal with things that has more than one output. And we kind of saw that on our trainer, right? You understand, when we came over here and we had four inverters, and then we did what? We said, okay, and we wanted to draw a truth table of the circuit. Well, that thing had 4 inputs and 4 outputs. And then you filled in the chart, right? So that was a circuit, not very complicated. Well, the way we calculate the number of possible input combinations is we count the number of inputs, 1, 2, 3, 4, 5, 6, and I'd say 2 raised to the 6th power, and this would give us the number of possible combinations we could put on those inputs, which would be what? 64, right? So we wouldn't do a truth table with 64 inputs, but now we've got a pretty good idea of how many combinations we could possibly put on that gate, right? So far, we are, I think the biggest one we've dealt with so far is 4 inputs, which gave us 16 combinations. Well, exclusive ORs, of course, are only going to have 4 combinations. But when we start sending digital data, we're going to be dealing with information. Normally, what we do is we have 2 methods we can send the data. We can send it in parallel, or we can send it in serial. Now, what advantage does each have over the other? Yeah, one is faster and one is cheaper. Using the same technology. Now, we have serial communications now that would just beat up on the old parallel data that we use. So a lot of our information now is the high-speed serial, but we could do it with parallel, but it's no need using parallel if it exceeds the speed capabilities of the media or the devices that we're trying to communicate with. Like this keyboard over here. There's no way in the world this keyboard needs to communicate with the processor or the computer in parallel, because how fast can I type? Right? Huh? Well, I can type pretty fast relative to other humans, but relative to a computer. One of the Star Wars movies, when the Data almost went over to the dark side, they asked him, how long did it take you? And he said, I thought it was only so many milliseconds. And Picard said, well, that wasn't long. And he said, well, that's an infinite amount of time to an android, to a computer. And that's basically what we're talking about here. So we've gone to serial on a lot of things, but what we need to do is we're sending this information over media. And what is media, by the way? Now, what's media? We hear multimedia all the time. What is media? Media is what information flows through. So what media am I using right now? What? Air. I'm using air. Air is the media. I'm sending sound waves through the media. And it happens all the time where you say something and people don't hear what you say, right? But what we're trying to do in digital, that could be drastic, so they had to come up some type of way that could very easily verify that the information being received was the information being transmitted, especially when we're using electricity. So the first method they came up with, and this is when we had 8-bit computers. So that's why when they came up with the first code to be able to represent not only data but also numbers, that we call the American Standard Code for Information Energy Standard, right? ASCII. This was originally a 7-bit code, even though we're dealing with 8-bit devices. Now, what they decided to do was to sacrifice 1 bit for error checking and for error checking. So what they did is they called that the parity bit. So we'd come up and we'd send out a code like this, and that code would represent something. We could look that up on the data chart, right? Understand? On our ASCII code chart. So what am I sending you? Anybody got their ASCII code chart? So if I was to convert this over to hex, which makes it a lot easier to deal with, this would be 56 base 16. It's going to be a lowercase letter, right? Y'all got it? What's that? Capital B? Really? So I'd send this over. But what they did, B, yeah, okay. I thought it was further down the line than that. Yeah, because uppercase B would be a. So this is an uppercase V. Well, what they would do is they would sacrifice this bit right here for parity. Now there's only two things I could do with that bit. I can either make it a 1 or I can make it a 0. So what they did is they came up with, okay, I come up here and I count the number of ones. There's 1, 2, 3, 4 ones in the actual code itself. So this is the ASCII code. Now we got 2 parities that we can run, and your transmitter and your receiver have to be set up for exactly the same parity. So we come up here, if this guy here was set up to generate odd parity, then this receiver would be receiving odd parity. So what the parity bit would do, if I'm running odd parity, then the transmitter would either put a 1, would set this bit, or clear this bit to make the total number of ones in the byte always odd. So if I was running odd parity, it would go 1, 2, 3, 4. That's an even number. What do I need to do to make it an odd number of ones? The parity bit would be a 1. That looks like oh yeah. Now it has nothing to do with even and odd numbers. It's the total number of ones being transmitted. So this is the parity bit right there. So this is parity. So it'd go 1, 2, 3, 4, 5. This is an odd number. It would send it over to the other guy. The receiver would count the number of ones. If it was odd, then the receiver would accept the data. If it was even, and it would send back a code for called acknowledge. So you look over in the first two columns, those are control codes. He would say, I acknowledge that, which means it received an odd number of ones. If it didn't receive it, it would send back a not acknowledge. We used to call it an ACK and a NAC. And then the transmitter would retransmit the data. That makes sense? So now we had a method where we could transmit data, and this was about 95% accurate. So every once in a while your printer would print a strange character because the problem with parity, it would detect a single bit change, but if two of the bits in the transmitted data changed, it would still say it was okay. So I transmit, this is the data being transmitted, and something happened, and this bit right here changed states, then it would go 1, 2, 3, 4, 5, 6. I'm expecting what? An odd number of ones, and I received an even number. So it would go back and it would say not acknowledged, and the guy would retransmit the data. But if something happened and two bits changed, 1, 2, 3, 4, 1, 2, 3, 4, 5, it would say the data would be okay. So that was the problem with parity. So your mass storage devices now really don't use parity. They use something called a CRC, cycle redundancy code. But it sacrifices a lot more bits. But what we do now with our mass storage devices, we transmit what we call packets, which is a groups of ones and zeros, so we can sacrifice a lot more bits. But this is still used, but not as often as it was. So the internet does not use parity, and your mass storage devices like USB drives and stuff like that doesn't use parity. It uses something called a CRC. Redundancy, yeah, CY. Cycle redundancy code, CRC. Cyclic redundancy code. But we're dealing with parity. So what they had to do is they had to come up with some type of circuit that would automatically generate and detect parity. Or equality, right? You understand that? So guess what they use? They use generators instead of parity generators. So what we need to do is just come up with a 4-bit number. Okay. So this is what I'm trying to send, and then we're going to add another bit up here that we call the parity bit. So these are the two 4-bit, nope, that's too many bits, Rich. Almost made a mistake again. So we're sending two 4-bit binary numbers. I'm sorry, one 4-bit binary number. 1, 0, 1, 1, and 1, 0, 1, 1. Then what this circuit is going to do, it's going to add a 5th bit that we call the parity bit. So what would I get out of this one? What would I get out of this one? What would I get out of this one? Okay. So 1, 2, 3, 4. So this guy should generate even parity. And then over here, this will give me a 1, a 0. What would I get out of this one? A 0. 1, 2, 3. This is generating odd parity. this circuit on the left is even parity. So we can come up here and see if this is going to work. So let's come up here and put a so I started off with 3 ones, right? So let's just put 2 ones. So if this is right, this right here should make the parity bit a 0, and this right here should make the parity bit a 1, right? So this one over here will give me a what? This will be a 0. This will be a get 0. This will give me a 1. No, I'm sorry. Give me a 0. Thank you. This right here will give me a what? 1. So this is the parity bit. This is the parity bit. So this is transmit 4 bits, which gives us 16-bit combinations for our code, and then we sacrifice. So normally a 5-bit number would give me 32 combinations, but what we're doing is we're sacrificing 16 combinations for what? Parity. That makes sense? Yes or no? Huh? So what I would do is I would send this. So this circuit right here, I would always send a what? An even number of 1s. This circuit right here would always send an odd what? Number of 1s. So we could come up here and put a truth table up here and do all the 16 combinations I could put on it, and we'd find out the circuit on the left always sends an even number of 1s. The circuit on the right would always send an odd number of 1s for all 16 combinations.
So regardless of what is parity or gate, whatever it is, and then the truth table is just that, a truth table.
So here I would come up with my 16 combinations using 4 bits, right? 2, 3, 4, 5, 6, 7. I'm gonna run out of room. 8, 9, 10. But what we would find out is this bit right here would be the what? The parity bit. Okay, but we got 2 different circuits. We got one that generates odd parity, and we got one that generates even parity. Now, what we have to do is when we send this, so what I would do is I would bring in my 4 bits on one side, and my parity circuit would generate 5 bits, with 1 bit being what? Parity bit. This would go over to my receiver. Before my receiver accepts the data, right, you understand, it would have to be what it's running. So if this circuit right here, if I'm using my circuit that generates even parity, then this guy's going to have a circuit that detects what? Even parity. And if a bit changes in the transmission, then it would say that it's the wrong data, right? You understand? If 2 bits change, and this is the problem we had with parity, is that if we had a 2-bit change, parity wouldn't detect it. All it did, it would detect a single bit change. Well, over time, it was proved that was 95% of the time. So parity was basically about 95% accurate. So but 95% accurate is pretty good for like printing information to a printer. But when saving information like on a hard drive or a USB drive or something like that, or sending information over the internet, we can't live with a 95% error. We won't. So CRC, a 16-bit CRC is like 99.999% accurate. So that means there's still things can get through, but it's highly unlikely. So 16-bit CRC is usually 32-bit CRC is, which means you use 32 bits for error check. It's a mathematical formula, guys. I'm not going to get into it. But what we do now is when I send information, when we send information over the internet, through the network, how often is this computer right here on the network? Is it transmitting, receiving data on the network right now? No, it's not. So what they said, well, so they came up with a technique, and we've only got 2 wires to send this on. So they came up with different methods that they can transmit and receive data. The first type of method they used was something that we referred to as a let me get my brain. We refer to it as baseband, which most of y'all don't understand. Most of y'all the difference. Y'all probably hear broadband all the time. But baseband was the first way we did that. Now baseband means that we have only one person is on, only one computer's on the subnet of the network at any one time. So instead of me sending bits, what we do is we send groups of data, like we arrange it in what we call a packet. And I would send 4,096 bits worth of data. Well, now instead of using parity, we sacrifice 16 bits for something we call a CRC code, which is basically better, right? Because 4,096 would be how many bytes? Well, if I was using parity, we would have 1 parity bit per byte. But if I'm sending 4,096 bits, right? Y'all understand? Then I can sacrifice 2 bytes of data for CRC codes. And the CRC code, a 16-bit CRC code, so I sacrifice 16 bits to be 99.999% accurate. Your hard drives, I don't know what USB uses. I don't know if they use CRC16. And this code, by the way, would be very, very accurate. So now I would know if I had an error in my transmission, right? You understand? So when I save data on a USB drive, I don't want it to be 95% accurate. I want it to be what? Very, very, very accurate. Now we can't, it's real hard to be 100% accurate. So 4,096, if I went to 32-bit CRC, which is what we use on hard drives, I'm still transferring information 4,096 bits, right? You understand? Which would be how many bytes? And we plug that into our calculator. So it'd be 4,096 divided by 8. 256 bytes. No. 64 bytes. Huh? 512 bytes. So if I was gonna use parity, then every 8 bits or every byte would have a parity bit. So that means I'd have 512 bits using parity. Using 16-bit CRC, I send it in a block of 496 bits. Then I sacrifice 16 bits. So it's more efficient. So we're using less bits to get what? To get better accuracy. And 32-bit CRC, guys, that's 32 bits. If for every byte of information you put on your USB drive, if I was using parity, we would sacrifice 1 bit per byte, right? You understand? Here we're sacrificing 32 bits, but your hard drive does it in increments of of 2048, yeah. So we do it in what we call packets. So this is what we use on our networking. Even though it's serial, we send it in packets. So I come up here and I ask to download a file. Well, what it does, it sends it in packets. And this is the way it works, guys. You'll send a packet, you release the network. And then somebody else is out there waiting on the network, right? Then they come in, they get access to it, then they release the network. So 4,096 bits at a time. Broadband means we modulate the data. And then we modulate the data, we can come up here, we can share the bandwidth of the media. Does that make sense? So we place it on the carrier. And that's what a modem is. So what is a modem? What does modem stand for? Anybody know? Modulator, demodulator. So modulator is the technique that we take information and we put it on something called a carrier, which is usually a high frequency. And then we shoot it out, right? So basically the way broadband, so baseband, which one's fastest? Baseband or broadband? Probably not. It all depends. So baseband, the less people that's on your network, the more bandwidth you get. Because you send 4,096 bits, you come off the line, nobody's on there, you send 4,096 bits for that 4,096 bits. If I'm using broadband and I've got a 10 megahertz of bandwidth, that means if 10 people is on that thing at a time, what you get is you get 1 megahertz bandwidth, period, because you're modulating. So broadband, you have a better chance of getting on the network. So the problem with baseband, the more people that's on there, the harder it is to get on the network. So you see ours pop up every once in a while. We got a real poor network, by the way. It pops up and says, what does it say? Network busy or something like that. And that's because this is baseband. Because a lot of people are trying to do what? Use the network at the same time. Baseband, you're almost guaranteed time, but you don't get the bandwidth you get if there's nobody on the network. So if you got a bandwidth of 200 megahertz, you get 200 megahertz, whether it's what? Whether if you're the only one on the network or there's 100 people on the network. But if I got that entire, 10 people, that would give me a gigahertz worth of bandwidth if I had baseband, if nobody else was on the network. That makes sense. And then plus broadband. If you've only got 10 reservations on there, then that means only 10 people could share it at the same time. So even on broadband, you can tell like in the morning, real early in the morning, you don't get the same data speed as you do late at night. And that's why most gamers that play online, they usually play when? After 12 o'clock, yeah. Because even though it's broadband. So CRC, we still use parity, but we don't use parity as much now as we used to. What does this guy do? This is a parity generator too. What's nice about this circuit is this circuit we just keep adding exclusive OR gates or NOR gates, depending on whether we use odd parity or whether we want to use even parity. Everybody okay? So one thing that a exclusive OR gates and exclusive NOR gates can do is they can generate parity.
And that's off of each other, correct?
Huh?
That's off of each other, correct? Like
You have to have one OR gate per bit.
gotcha.
I mean per 2 bits, right?
Yeah.
Yeah. So here we could do a 4-bit parity. We can trace this through. So let's just real quick. Let's just come up with a 4-bit number. So this would be 1, 1. This would be 0. This would be 1. So this is what I'm sending. And let's see what would I get out of this one? Be a 0, right? And that what would I get out of this one? And what would I get out of this one? Yeah, so this guy generates odd parity. But all I have to do is just change this from an exclusive NOR over to an exclusive OR, and it would generate even parity. So this is a little simpler circuit than the other. Oh, I'm sorry. You're right. Be a zero, right? So this guy generates what? Yeah, that's a NOR. So this guy generates odd parity. So pretty simple circuit. But what you have to understand, parity is used so often that what do you think they've done? Well, they've integrated all these things into a what? Into a single integrated circuit.
Now, I know on the other one where it shows the NOR, they had a diamond in there. Does the diamond make a difference?
No, it's just that they had a problem drawing a circuit.
Yeah.
So good point. So this is a 74280. This is a parity generator. It's either got an exclusive OR output or an exclusive NOR output. Here, it transmits 8 bits, and then what we do on this one, the transmitter, we connect the 8th bit to common, right? You understand? And then we send that over, and if we want to use even parity, we just use the pin that's designated for what? Even, yeah. So if I was going to use even parity, then what I would do is I would send this over on bit A. If I was generating odd parity, which is what this one do, they just send this over on pin A. Now on my receiver, I use all 9 pins. On here, I do what? I connect I0 to common, and then this guy right here would come in, and it would indicate whether I had if I was using odd. So here we're generating odd parity, so we're going to detect odd parity. But if I wanted to generate even parity, then on my other circuit I'd have to detect even parity. So this guy right here, it's all it is a bunch of exclusive ORs. So if we look this up and looked up the datagram, actually the internal circuit, we'd see a bunch of exclusive ORs in here. And all we have to do is just on one circuit, this output, so this is an even parity generator, right? So on this guy, we would output off an exclusive, exclusive NOR. On this one, all we do is just output on exclusive OR. Now what makes this thing up? Well, I don't care what makes this thing up. All I know is it's a what? It's a parity generator and checker. We use the same circuit for this. So we're trying to transmit this data. And of course, we're transmitting the data on 1, 2, 3, 4, 5, 6, 7, 8 wires. And then we sacrifice this 9th wire for what? For parity. But we only add one more conductor to be 95% accurate on that the data transmitted is the same data that's been what? Received. So one of the functions of exclusive ORs and exclusive NORs is being able to do what? Generate and detect parity. That makes sense? Everybody okay? Parallel parity generators. Another thing that we can do with an exclusive OR, you find my blank sheet. We ran into this. So what do we use on our oscilloscope to put our oscilloscope in sync with the information being received on the inputs of the scope probe? We call it a trigger, right? You understand? So when I send information from here to there, and I'm sending it in pictures, what would happen if those pictures are out of sync? Well, either the thing is going to lay down on its side or it's going to roll on. So what they do is the video sends 2 sync pulses. it sends what we call a horizontal sync and a vertical sync. So there's two sync pulses included in the video that we're seeing. And what this does, it synchronizes. So a lot of people don't know that video is transmitted one line at a time. And then when we get over to this side, what do we want to do? We want to tell our receiver that we've finished transmitting a line. And then it would drop down to another one and 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 another one. At the end of each one of these, we need to synchronize to tell our receiver when to reset back over to the left. Does this make sense? Now when we get down to the bottom, we need to send two sync pulses. We need to say, okay, I finished the line, and we need to have another input saying I finished the picture, right? Does that make sense? So we have what we call vertical and horizontal syncs on our video. So the horizontal would give us a sync every time we got to the end of the line. The vertical would tell my projector over there to reset everything back to the wall, up to the top left. And that's what you're doing when you specify the resolution on your display. Okay. So what we're doing, we're synchronizing this, right? Does that make sense so far? So, but what they had was, when they first came out with the video between the computers, is that some monitors looked at sync pulses that were like this. Some monitors looked at sync pulses that was like that. So what we had to do is we had to go into our video card, and there was a little switch on it that if we plugged it in and plugged the monitor to it and it came up out of sync, then it probably told us what? That we needed to invert the sync pulses. Now over time this has disappeared, so we had to come up with some way that we could have what we call them programmable inverters. By the way, another thing, and we've looked at this a little bit. So this is a symbol of what do we call this circuit right here? We call it an inverter. An inverter does not logic, right? Okay. Then what would that be the symbol of? We've already talked about this once in class. This is not one of our 5 basic gates because it does no logic. It's not a not because it doesn't do not logic. But we use them. We've already talked about this once. This is what we refer to as a buffer. So let's see if we can. But it doesn't do a logic function, so we don't consider it to be one of our five basic gates. So we're dealing with a 7404, which is a hex inverter, right? Wow, I don't have one. Seems like I should. So what's this guy? Up above it. This is a hex one, but it's a driver too. So notice here's the symbol right here. Has basically the same pin out as the 7404, but here this guy does no logic, but it's a buffer. What does buffer mean? Well, it means it's a go-between, right? Y'all understand? So we're going to use this for several different things. One thing we're going to use it for is for isolation, just isolating things. But what we wanted to do is we wanted to have a circuit which I could make act like a buffer, or I could make it act like an inverter. So what we did, the way this circuit worked, now notice here that this guy also uses, they don't use slopes. Undoubtedly they had a problem drawing the curve. So what I'm going to do is I'm going to bring this signal. So this is the signal I'm bringing in. And what I'm going to do is I'm going to come over here and bring this over. Pull-up resistor. It's going to be plus 5 volts. So if I don't have the switch closed, so if I have the switch open, then what would we get right here? We would get a 1, right? Understand that. If I close the switch, I would get a what? 0. And we don't like to leave an input of any gate floating. So here we're going to get a true high, or we're going to get a true low. Do you understand that? So if I was to come over here and do this, and then I come over here and put the switch right there. So what would I get if the switch was open? I would get a nothing. We don't know. So this is why we never do it like this. So what we do is, if I want to control a high and a low with a switch, I do it through a pull-up resistor. So that way, if I open the switch, I don't ever get a nothing, right? You understand? In fact, technically we call this a float, a floating input, and we don't like floating inputs. So you'll see a lot of switches used in digital, but they're going to do it like this. They're not going to do it like this. So if I open that switch, I get a nothing. I don't get a high. I don't get a low. Because a low is 0 volts. It's not a nothing. It's 0 volts, right? You understand? And when I open the switch, so here we don't know. We don't have any idea what this thing is going to accept a watt as. A nothing. So we don't leave. We had a scale down in Calera, where on real cold days, it wouldn't work. On hot and warm days, it would. So in the wintertime, we would go down there. By the time, and it was out in a shed. And so what would happen is, the sun would come up and it would hit the shed and it would warm the scale up, the digital indicator up, and it would start working. At night, when there was no sun shining on the shed, the thing gave us the wrong thing. And guess what we found? Some engineer left a input to one of those logic gates floating. Nothing. Well, that's not floating. That's a clock signal. Yeah. Well, that's what they're going to say. Would you get a clock out? Would you get a nothing out? This is one we're trying to use a AND gates and OR gates. But an AND gate will always be an AND gate, and an OR gate would always be an OR gate. What we can do with this guy is so what we're trying to do out of this thing is we're trying to get this function, or we're trying to get this function out of this input right here. So that right now I would have a 1 right here, right? You understand? Yes or no? So if the input, so here's my signal. So I'm gonna put a 1 on my signal. I've got a 1 on my other input. So what would the output give me? A 0. So if I'm looking at this as my circuit, I put a 1 in, I got a 0 out. So if the input went to 0, the output would go to what? 1. So what I'm going to do now is I'm going to come up here and close the switch. So that's always going to put a what right there? A 0. So now if I put a 1 right here, the output would give me a what? A 1, because they're not equal, right? You understand? So 1 in gives me a 1 out. If I come over here and make this a 0, then my output would go to what? A 0. So now it's acting like this guy. Before it was acting like what? Like that guy right there. We're talking about from here to there. So we can use this guy. We call them programmable. They're called programmable inverters. But you decide by flipping a switch whether you make them do what? Whether you make it invert or you make it not invert. And that's what they're showing you in this picture right here in the book. This guy right here. So what I'm doing is I'm coming up here and I'm either going to put a what? I'm going to put a 1 there. If I put a 1 there, then all 8 of these are going to act like inverters. If I put a 0 there, then all 8 of them is going to act like buffers. And this is what we had on our video. This is all we had on that video part. So I would come up here. It just had a bunch of exclusive ORs. I can show y'all the schematic later on. They're in there in that big blue book. And you'll see that switch. We flip a switch, and what it would do is it would let the horizontal sink come through and be a positive pulse. If I flipped it, it would go what? It would convert it over to a negative. So we can use them as what we refer to as controlled inverters, is what the book calls them. So technically, they're not always inverters. It's we're going to make them inverters or we're going to make them act like buffers, right? Now, what's the third thing we can do with exclusive ORs? So we can check for equality, right? We can use them to check parity. We can use them to be controlled inverters. And the third thing we can do is we can, oh, by the way, this is we're going to be dealing with a 7485, which is a 4-bit comparator. I have no idea where this is. This is not a good diagram of that. This is better. I don't know where these data sheets from in the book come from, but I've never seen one that has this nomenclature right here. This is the one I'm very familiar with, where we have a set of inputs called A and B. So what this guy's doing is comparing A0 to what? B0. It's going to compare A1 to B1, A2 to B2. This is what I was trying to do on the parity generator, by the way. A2 to B3. And then what it's going to do, it's going to generate an output that says what? A equals B. And it also lets us know if what? A is greater than B, or it lets us know what's what? B is greater than A. Generates three outputs. Now what they're doing here is they're showing it how they could be what? Cascaded. So I can take the A, B, C, D output of this one and bring it into A, B, C, D, A to the equal to, greater than, or less than this. And then I could bring in four more binary bits. So this would be an 8-bit comparator. I worked on a milling machine at Beach's Machinery. Y'all know where Beach's Machinery is at? You see it on the interstate. When you go up the interstate in Fairfield, it's on the right hand side. Got big beaches up there, and they had a milling machine up there, and it was extremely old. And all the logic was done with individual transistors. So instead of using integrated circuits, them boards had hundreds of transistors. And what they would do is they would come up here on a panel, is they would set a 0, and they would come over here and they'd put an X, Y, Z, and then they would tell it to mill between those 2 points. I know what a milling machine. What's a milling machine? Anybody know what a milling machine does? The difference between a milling machine and a drill. And a drill press. So we got drill presses. We make those in numerical control, and then we have what we call milling machine. It's a former. It cuts grooves. It smooths off the side of an object. So it's not meant to drill through. It's meant to put grooves in objects. It's meant to smooth out things. So you got different shave. It shaves a little bit off. Yeah. So this was a big old milling machine. I mean, it was huge. And what happened was, and it had a sensor on there that while the XYZ moved, it would send pulses out. And then the pulses would go through a counter, and then we would compare what the operator set those thumb wheel switches. It would compare it to the counter, and when they would equal, it would know it was at the right spot. But all the comparators were done with nothing but transistors. And we came in, and one of the sets of transistors were bad. So what do you think I did? I replaced it. I glued it on and set it up and replaced the whole section with 7485. As far as I know, the milling machine is still working. But I forgot how many bits of comparing that we did, but I used almost the same circuit. So 7485, and so I have the need to compare information. We do that all the time. So I set something over here, and then I want to see when it's what? When it's equal, or if it's not equal, right? And stuff like that. Does that make sense? So if A was greater than B, what it would do is it might tell the milling machine to go from left to right. If B was greater than, if it was opposite, it would tell the machine to go what? Right to left. And when they were equal, it would do what? Stop. It would know they were equal. So I could do this with a bunch of logic circuits, or I could do what? Or I could buy 7485, and all this is already in there for me. Well, these guys are very, very popular. And there's the diagram of 7485. Do I need to know that? And notice these are exclusive circuits. If we went back to our original, I don't need to know that. Why? Because if this output right here goes bad, what do I do? I replace this. Y'all understand? So we'll look at some things, and we've got to understand how these things right here work. So these are exclusive circuits right here. Okay, so this actually shows the makeup of an exclusive OR, which is way back here at the very start. But I don't even need to know that. Why don't I need to know that? I don't need to know what makes up an exclusive OR or what makes up an exclusive. I don't need to know what makes up this guy right here. This is going to be a bunch of transistors. All I need to know is how this thing right here works. If it don't do what it's supposed to do, I don't go in there and replace an AND gate. I don't go in there and replace an OR gate. I just place the whole wall, the whole thing. So I don't need to know that this is what makes up a 7485. I don't need to know that. I don't need to know that. Why? All I got to do is understand how this thing right here works. And if it don't, but I got to know how this works, right? You understand? And this is definitely a combinational logic circuit, but what's it made up of? It's made up of the 5 basic gates.
So how do you know that those difference between the NOR and the each NOR? Because on that schematic, it seems like that's the actual.
But we don't need to know that.
Okay.
All we need to know is what this guy right here does.
Okay.
All we got to do is know the truth table or know what this guy. It's a comparator, right? Y'all understand? I don't need to know that the makeup of this circuit right here is this guy right here. God, it's kind of fast, guys. So this would be the actual transistor makeup. I drew that backwards. Now we're going to learn a little bit about this. We don't need to really understand it a lot, but it's going to help us troubleshoot. So all this goes back to VCC, and we have one up here. This goes right here. So this is the makeup of that gate right there. Do I need to know that? Right? You understand? So what happens if this guy right here goes bad? Well, that's going to cause one of these outputs to do what? It's going to cause one of them outputs to go bad. If I understand the operation of the entire circuit, right? You understand? If it don't do what it's supposed to do, I don't go in there and replace a what? A transistor, because I can't, because it's all part of an integrated circuit. What do? I replace the whole thing. So that's what we're trying to teach, is the operation of these different circuits. So this is definitely a combinational logic circuit, but if you look at every symbol inside that, it's made up of nothing but the basic gates. And of course here they're drawing these as negative NAND, but actually they're NOR gates, right? You understand? But in this circuit, these guys are looking for all lows to get a high. They're not looking for any high to get a low, right? You understand? But I'm not concerned with that. All I know is if the two inputs are equal, so if somehow I could come up here and put equal inputs on this thing, and then and this right here does not do what it's supposed to do, then I would do what? I would replace the what? The whole integrated circuit. Right? That makes sense? So if I got my milling machine and I put a number over here and it keeps flying, it goes from left to right and it keeps flying, and it don't stop when they're equal, then I know I've probably got a problem with this guy right here, right? Either that or one of these inputs over here are messed up. So that would be what I would come up and figure this out. So I don't need to know the actual makeup of these things. All I need to know is what the guy does. What is it supposed to do? If it don't do what it's supposed to do, I don't go in there and replace a single transistor. I don't go in there and replace a single gate. I just replace the whole item. And this is the last thing. I know we need to do some lab today. Let's just do 2 bits. Let's say I want to add 2 bits. So if I add a 0 plus a 0, what would that give me? 0. If I was to add a 1 plus a 0, what would that give me? A 1 plus a 0. 1.
Oh, you're talking about the binary.
Yeah, this is binary. This is basic binary arithmetic. A 0 plus a 1 would give me a what? 1. A 1 plus a 1 would give me a what? Give me a 0 with a carry of 1. Well, if I was to convert this over to decimal, this would be equal to a 2. So 1 plus 1 is a 2, right? You understand? So if I was to come up here and add these two binary numbers right here, this would be a 0 with a carry 1. This would be a 3. This would be a 1 with a carry 1. This would be a 0 with a carry 1. This would be a 0 with a carry 1. This would be a 0 with a carry 1. And this would be a 0 with a carry 1. So to me, binary math is a lot easier than what? Decimal math. Because you don't have to remember that, 7 plus 5 is 12. All you got to know is that all I'm dealing with is what? Ones and zeros. But we do the same thing, right? That makes sense. So it would be nice if I could come up with a circuit that would do this math. So what circuit would give us this right here? So what we're going to do is going to do away with the carry. So when they're not equal, I get a 1. When they are equal, I would get a 0. So let's see, I come up here and I put a 0, 0. What's a 0, 0? This is the exclusive OR. 0. Let's come over here and let's say, what would I get? Huh? They're all the same. This symbol right here tells me what I get when they are not equal. So this symbol right here would tell me I get a 0 if they're not equal. This symbol tells me I get a 1 if they're not equal. So what the output on the symbol does, it tells you what we get when they are not equal. So if I was to come over here and put a 0 and a 0, what would I get? Well, they are equal, right? You understand? So I'd get a what? 0. Because it says I get a 1 if they're not equal. Well, see, that matches that right there. If I come over here and do a 1, 0, they're not equal, so what would I get? I get a 1. Which matches that one right there. If I come over here and put a 0, 1, I get that one, which matches that right there. If I come up here and put a 1, 1, I get a 0, which matches this right here. So what would happen if I came over here and tapped off right here and tapped off right there and put an AND gate right there? Then this last one would give you that right there. So this little circuit right here would add 2 binary bits. So this is called an adder. It's called a half adder. It's called a half adder because it can't pick up a carry. Does that make sense? So if I was going to try to add this plus another number, then I've got problems because this circuit only does that right there. But what I would do is, let's say I got 1, 1, and then 1, 1. Well, this circuit would do this, but it would have a problem with the next bit, right? You understand? Because I've got to be able to bring a carry into the next bit. So this would be the one I just did. This is called a half adder, and then this right here is called a full adder. So what this does is it brings in the what? The carry from the previous bit, And then it would do what? Then I could add the two numbers, right? You understand that? Does that make sense? So this guy right here, we're not going to go over the circuit. We're just going to say this whole circuit right here, because we're not going to use these guys to add. What are we going to do? We're going to buy an integrated circuit that does what for us? Adds. That makes sense? So a half adder, what it will do, it'll add two binary bits and it'll generate a carry, but then we got to come up with another circuit that would take the carry. Does that make sense? So down here, I would bring in two numbers, and then this would be a half adder, and then this would generate a what? This would generate an answer for this bit, and this would generate a carry, and then I would bring this into a what? A full adder. This would generate a carry, and then I would generate a full adder. So you'd use a half adder on your least significant bit, and then from then on you'd use full adders, and then we could come up with a way to add binary numbers. But this would be a lot of circuits when we probably understand that I can go out and I can buy an adder circuit. I think it's a 74-181, I think. See what it is. Does your book tell you what the adder is that they got in the book? So what I'm trying to say is I come up with a circuit. The circuits are made of the basic gates, and if the circuits are used if the circuits are used often enough, what are they going to do eventually? They're going to integrate them. So the first computers we worked on, if you looked at the motherboard, and I might have the motherboards up here, that suckers had integrated circuits all over it. But over time, the computers became so standardized. So what do we have in this computer right here? We got a processor, right? And which is still unique. The processor is about the only chip in there that's basically unique. But and that's not true. It's when I first worked on computers, our central processor, it was what we call a mini computer. So we only had two versions of computers when I first worked on them. We have what we call mini computers, and then we have what we call mainframes. And there was no such thing as a personal computer. And we looked at the CPU. The CPU board was the central processing unit, was actually three big old circuits, because everything was done with nothing but what we're going through in this class. But over time, they said, wait a minute, why can't we miniaturize that? Why can't we take the arithmetic logic unit, the instruction decoder? Why can't we take the bus drivers and all this kind of stuff and integrate it into a single package? And this became known as a microprocessor. Now the problem is when they started integrating all this into a single package, what do you think they sacrificed? Well, the first processors, the first processor that came out was a 4-bit processor. So it only processed 4 bits at a time. And then the next processor that came out went up to an 8-bit processor. But what we did, guys, is we sacrificed speed. So a microprocessor will never run as fast. And the problem we have is we have this thing called software, and we have this thing we call hardware. So hardware means you do everything, you can touch it, right? You understand? Software is non-touchable. Okay. Hardware will always be faster than running things with software. So anytime we start turning things over to programs, then we're going to slow down speed. So this is why your big supercomputers and stuff like that basically still use what? They still use integrated circuits. They use individual integrated circuits. So the CPU on a supercomputer is going to be huge. The CPU on my cell phone is what? Small. These guys right here, we're looking at maybe, 1 million or so instructions per second. Supercomputers do well over 10 billion instructions per second. So we got 2 supercomputers in the state of Alabama that I know of. And they're both in universities. We got one in the University of North Alabama, and I think they got one down in the University of South Alabama. But what happens is, originally we had all these chips, but these computers do the same thing. So what started happening is all these functions started doing what? Integrated into integrated circuits. So I wish I could find that old motherboard and let y'all compare that to a new motherboard. Y'all know what the motherboard is, right? What is that?
This is the brain of the computer.
Well, it's what makes up the computer. The motherboard is what makes up the computer, right? So what we have basically inside the computer, y'all know the basic makeup of a computer. Well, processor would be on the motherboard. Hard drives wouldn't be part. Hard drives are considered to be peripherals. They're not part of the computer. So somewhere out here we got a what? We got a central processing unit. And what else you think we got?
Oh no, because everything I be saying, you keep shutting me down.
Power supplies wouldn't be. It's attached to the computer, but we're looking at what makes up the motherboard. The motherboard doesn't have the power supply. So the motherboard on this one don't have a power supply, right? Where's the power supply at? It's external, right? Anybody know what else we got? We'll crawl. So we got a CPU somewhere, at least one, right? Now we have what we call cores. So basically, when we first came out with our server, we need to go lab. This is our first file server, by the way, right here. Our first domain server.